Thanks for coming out on this bright sunny day where spring has visited us temporarily once again. Nice to see spring coming, although in February gets me a little worried. My name's Hal Roth. I direct the Contemplative Studies Initiative and Concentration here at Brown. And let me see, how many of you are new to contemplative studies? Okay, is that enough justification for going into the explanation of what contemplative studies? Maybe.
Yes.
Yes? We are one of the newest concentrations at Brown, and we study contemplative experience across cultures and across time from scientific, humanistic, and artistic perspectives. We also teach contemplative practices in a very particular way in the classroom setting, in which students not only approach studying contemplative practices from the at-a-distance perspective of a third-person observer, which is what we do in many of our classes in university, but in particular we emphasize what we call a critical first-person perspective. So that is, we learn the techniques that we would learn in a contemplative practice center. We learn the cognitive frameworks in which those practices are embedded. But we also subject those frameworks to the kinds of criticisms that one does not ordinarily do in a contemplative practice center. And we don't expect students, we don't ask students, we don't require students to believe in the veridicality of those cognitive frameworks. They're up for grabs, they're up for study, they're up for criticism, they're up for discussion, based on students' own experience and based on the kind of the learning and research in humanities and in sciences that have been gathered on contemplative practices and that we study in these courses. We have a very active series of lectures and events. We have the next two events coming up. Actually, we have three events coming up in the week starting on Sunday, the 24th of February. We have an all-day introduction to Rinzai Zen meditation with Taka Kawakami, who is an abbot of a Zen center in Kyoto that Gaelle and I both, Gaelle and I worked together on the planning committee for a conference that was held on the impact of cultural context on contemplative practice, which is something really important and very much worth studying, because a lot of the contemplative practices that are studied now in scientific context, in a sense, have been deracinated from their cultural context and historical and philosophical and religious contexts, and re-racinated within different types of modern contexts and non-spiritual, non-religious, non-cultural contexts over here. So we decided with this conference that we would see what, if we could, start to explore the impact of the decontextualization and recontextualization and the extent to which the practices change. So we had this wonderful conference, very much a kind of in the spirit of contemplative studies. And on the first before last day of the conference, we had a major typhoon blow through, Typhoon Jebi. And we all kind of huddled together in this Hanazono Kaikan, this kind of, what would you call it, kind of a guest house, hotel type place. And felt the power of Mother Nature shaking the rafters, blowing through the ventilation system. It was quite an experience. Anyway, the person in whose temple we stayed will be coming to Brown on the 24th and for all-day intro to Zen practice, and on the 25th he'll be giving a public lecture. And later that week, a very famous scholar of Chinese Buddhism, Peter Gregory, who had most of his career at Smith College, will be giving a lecture on Chinese Buddhism. A little bit later on in March, we will have the two leading scholars of Hatha Yoga in the world, James Mallinson and Mark Singleton, coming to Brown for 5 days, and there'll be two public lectures and a yoga workshop in the middle. So if you'd like to learn more about us, please go to our website. You can find it by just going to Brown and look on the A to Z, as we say in Canada, which is where we shared some experiences, although not together. And then you can sign up for the mailing list. So in talking to Gaelle this afternoon, Dr. Desbordes, I discovered that we both had what would I call formative academic experiences in the northern climes of Canada. Gaelle did a master's at Laval University in Quebec, and it turns out to be in computer science. Mm-hmm. And I had my first teaching job at the University of Alberta in Edmonton, replacing somebody who had gone on leave during the winter term, of course, during the winter term. And I think we both realized that maybe that teaching in a climate in which it was regularly minus 18 below as the high temperature might not be conducive to not only getting the body moving, but getting the mind moving as well. So Dr. Desbordes received her, I noticed, and look, I couldn't find at first your CV, but I actually found it and I looked it up in detail, and I see among your study in France is that you became, you got a degree from as engineer civil of mimes. And I
Mines.
Thought, oh, not mimes? Mines? Oh, sorry. Didn't have my reading glasses. I kind of wondered how you would be able to do that. And what your master's thesis would be. She received her Ph.D. at Boston University in cognitive and neural systems. She's currently an instructor in radiology at Harvard Medical School, and she's on the research staff in biomedical engineering at the Martinos Center at Mass General. She's a neuroscientist with a strong background in computer science and in engineering, and does a lot of research with brain imaging in the study of meditative practices. She's won quite a number of prestigious grants and published at least 24 articles, and is going to talk this afternoon on the neuroscience of meditation, which is one of her general areas of specialization. So without further ado and bad puns, please join me in welcoming Dr. Gaelle Desbordes.
Thank you, Hal, for the introduction. I'm glad I don't have to mime my talk. So yes, I am a neuroscientist and with a background as an engineer. And so now I'm studying meditation, but I'm bringing in this type of approach to my research. And so I wanted to talk today about neuroscience as a modern context in which we study meditation, kind of in line with how I was saying with decontextualizing and then recontextualizing these practices. Neuroscience itself has become a context. And so I want to present some ideas on how far really the field of neuroscience is in terms of investigating meditation. So the title is deliberately a little bit provocative, and I hope you'll forgive me, but you'll see what I'm trying to explain here. So first of all, I'd like to dedicate this talk to the memory of Eric Schwartz, who was professor at Boston University and who passed a few weeks ago. He was one of my mentors, and it's through him that I got into studying brain imaging, and especially brain imaging of meditation. So I owe him a great deal. So I just wanted to acknowledge that. And so I'm going to start with giving you a little bit of a big picture view of what neuroscience is. So for many people, neuroscience is this. It's modern brain imaging techniques in human, and we see these images all the time in the media, and this is what we know about brain, right? So in fact, this is really just one subdiscipline of neuroscience. Neuroscience investigates the brain on many different dimensions and scales. So for example, on the spatial scale, it goes from this kind of broad regions and area scale down to populations and ensembles of neurons, down to single cells in the brain. And there are people who are experts in all of these different spatial scales. Likewise, on the temporal scale, with brain imaging, typically we're looking on a time scale of a few seconds if we do functional imaging, but we can also look at development and lifespan and measure how brains changes as children grow and then as adults mature and then grow old. But one can also study from an evolutionary perspective how brains have evolved throughout these millions of years of evolution and how our human brain fits within that. Then there's also a different type of scale, which is topological, and that's the study of networks. So this is something that these brain imaging ways of showing the data really don't show very well. It gets very complicated. That's where computational modeling gets in, artificial intelligence methods. So I'm not going to get into that, but I just wanted to show you this big diagram to emphasize that we really, when we talk about neuroscience, it's really neurosciences. And there are many subdisciplines. They don't necessarily talk to each other. And the brain is really, really complicated, okay? So when you see a diagram like that, it seems a little simpler than what it really is, I guess, is my point. So then how do we apply this to studying something like meditation or like contemplative practices more generally? So here's the outline of what I would like to talk about today. So I'm not going to read it right now, but let's just begin with the first one. One of the first questions that was asked by neuroscientists interested in this was, how does the brain change over time in meditation practitioners? So this is linked to the concept of neuroplasticity, the idea that life experiences change our brain. So this is a very important concept in neuroscience. So I'm going to read you some of the known facts as of the state of knowledge today in neuroscience about neuroplasticity. So first of all, differences in genes and environments make the brain of each individual unique. So it's both genes and environment, okay? So genes do play a role. It's not just training and what happens in your life. Number two, most neurons are generated early and then survive for life. It's true that some neurons may be born even in adults, but it's only in very specific regions and in kind of specific functions, and it's not like the whole brain is constantly growing. Some injuries can harm nerve cells, but the brain can recover from either stress or damage or disease, and at that time kind of grow new pieces of brain to kind of recover from these. So this is really specific to brain injuries. The same mechanisms do not typically happen when there's no brain injury. Number four, continuously challenging the brain with physical and mental activity helps maintain its structure and function. It's a concept that's often summarized as use it or lose it. So you may have heard this in the context of meditation, neuroscience, that if you do meditation, it's going to somehow change your brain. You need to keep doing it in order to maintain the effects. That's beyond what the science so far has been actually looking at directly when it comes to meditation. So this is much more general. And note that this is also physical activity. So the effects of aerobic exercise, for example, are very well documented. And if you want something that's really good for your brain, so to speak, and that is science-backed, that has been validated in animal models, in humans, physical activity is it, okay? There's much more evidence for that than for meditation. Let's be clear. There's much more evidence that supports physical exercise than meditation for your health, including the health of your brain. Also, neuronal death is a natural part of development and aging. So the fact that some neurons die is not necessarily a problem or a disease or something bad. It may just be part of normal development and aging. And in fact, some conditions in which there's a lack of synaptic pruning and neuronal death, such as autism, show that it can become problematic to keep too much stuff in the brain, so to speak. So we should not necessarily automatically think, oh, we lost some gray matter or white matter, therefore it's bad. Maybe it's bad, but then maybe not. It's not that simple. And then finally, some neurons continue to be generated throughout life, and their production is regulated by hormones and experience. So that's the idea of neurogenesis that I mentioned earlier. So can we harness these principles of neuroplasticity, for example, with meditation practice? So that has been a major question in the field ever since people had the techniques to start looking at that in human. Remember that human brain imaging really is only a few decades old. Before then, the only methods available to really look at brains was to do animal studies and then to actually kill animals, take their brains out, slice them, look at them under a microscope, or you could also do some invasive stimulation or recordings while the animal was still alive by implanting electrodes and so on and so forth. So with humans, only fairly recently were brain imaging, non-invasive brain imaging methods available. So people were early interested in the effects of meditation. So for example, in this pioneering study by Sarah Lazar, published in 2005, she looked at differences in brain structure between people who were long-term practitioners of different styles of meditation and people who were not practitioners. And what she found was that possibly meditation might offset age-related thinning of some regions of cortex associated with attention, interoception, and sensory processing, including the insula here and the prefrontal cortex. So, so this is summarized here. So that was the first of a number of studies along the same lines. And more recently, these studies were summarized in a meta-analysis, meaning somebody took 21 of these studies together, which corresponded to about 300 subjects, and then run some special analysis on it to see if there was any results that were similar, that were repeatable across these different studies. And so they found, indeed, some regions in which there seemed to be consistent changes associated with the practice of meditation. Some of them associated with body awareness, insula, somatosensory cortices, some of them associated with memory and stress regulation, like the hippocampus, and then different parts of cortex associated with a sense of self, emotion regulation, intra and inter-hemispheric communication. So this makes it look like, well, there is scientific evidence that meditation can change the brain, right? And this was in a mix of studies. 15 of them were cross-sectional, meaning comparing two different groups of people, and 5 of them were longitudinal, meaning that they followed the same people pre to post some training in meditation, which is typically for 2 months, but I think there was some variety there too. So already here you can see that there's a lot of variability in the types of studies that were summarized here. But then, more problematic, all of these different changes were actually measured in different ways in the different studies. So what does it mean? In some of them, they looked at the volume of some of the brain areas. In some of them, they looked at concentration of gray or white matter. In some, they looked at thickness. In some, they looked at some measure of the integrity of the white matter. Or some measure of how convoluted cortex is. So you see that these measures have actually very little to do with each other. And it's a little hard to interpret what we're looking at when we're looking at a summary of all of these things put together. Isn't it a little bit like comparing apples and oranges? So there's a concern about the methodology here that is also just reflective of where the field is at right now. So I'm certainly not blaming the authors of this particular paper for doing it this way, because that's the types of studies that are out there that are published, and that's what they had to analyze. But with all of these different variables, it's really not clear which actual neural mechanisms underlie all of these different measures, and most likely it's different things. So in the end, it looks like we actually still need post-mortem studies in which we would need to study the brains of meditators after they die and then do some very classic histology and then measure things that we can directly see in the tissue. All of these MRI derivative measures are just very difficult to interpret. There are other challenges, actually, with measuring structural brain changes, especially over time. Even if we had a really good measure, like an instrument that just gives us really good and reliable and easy to interpret measure, there is variability in each individual's brain over their lifespan. For example, with aging, there's a global volume loss of 0.2% per year after age 35. If you think that's bad news, you're not alone. But you know, we're all managed to live way beyond that age anyway. So, and then these changes in thickness and volume are not uniform across the brain. So how do we account for that when we compare different meditators of different ages? Besides, does everyone age at the same rate? Exactly, probably not. There's even daily variability in measures of brain anatomy, which complicate things further. It can change with how much water or how much caffeine you've had. And these changes are very significant. I've seen that myself in data. It's a major confound that very few studies take into account. So what if you happen to have meditators who just had a lot of water and non-meditators who didn't, and then you think you're seeing a difference that's associated with their meditation practice, but it's not. Sleep quality also can change some of these metrics of brain anatomy. Hormonal levels, especially in women, it will follow the menstrual cycle. So this is just to point out that science is hard, and we do these brain imaging studies, we have results, it's great, but until it's replicated, until it's been demonstrated with multiple methods, until we've at least considered all possible confounds like this, we need to be careful with the conclusions. And also remember that when we say that meditation increases certain areas of the brain, is that a good thing necessarily? Like, we don't know. Again, just because something grows doesn't mean it's necessarily beneficial. Just because something shrinks doesn't necessarily mean it's not. It's just more subtle than that. Okay, so now the second type of question that people have asked with brain imaging studies of meditation is what is happening in the brain during meditation, or after people have meditated, does that affect their brain function? So I'm going to describe several studies, several landmark studies in the field, and then discuss them. So in this 2008 study, led by Richie Davidson, who's shown here, with Antoine Nutz, the first author, they looked at a brain activation when expert meditators engage in compassion meditation while listening to different types of sounds, either sounds of suffering, and it was like a woman screaming in fear, or sounds of happiness, and it was sounds of a baby cooing. So they had to basically do their compassion meditation in the scanner while they were given these sounds in some random order. And the scientists analyzed the brain response to what happened when they heard these sounds. So when they heard the sounds of the woman screaming in fear, the expert meditators, compared to people who were novices, actually had more emotional reactivity. They had a faster heartbeat, and they also had a stronger activation in this part of the brain, the insula. So the insula is a really interesting area because it comes up very often in meditation studies. but it also comes up very often in a whole lot of other studies and other types of tasks. And so this is very difficult to interpret on its own. Like when we see, okay, there's increased activation in the insula, what does that mean? You can come up with like many possible explanations. Why is that? First of all, the insula is not a single area with one single function. It actually is comprised of 3 different functional regions, like subregions. Here they're shown in this meta-analysis as 3 different colors. There's a posterior part, a dorsal-anterior part, and a ventral-anterior part. And more problematic for us, many different types of mental events or tasks can activate the insula. So here are shown, I hope you can see the words on the screen, some of the types of tasks that would engage, for example, here the ventral anterior insula, such as emotion, face, gustation, and then the dorsal anterior insula, cognitive tasks, inhibition, stimulation, switching, error processing, and then the posterior insula, things like pain, somatosensory, sensory motor, but also music, motor, auditory. So this is a whole lot of categories of different things. So if you see activation in the insula, you really don't know what that means on its own. And that's something that is actually true across many, or most areas of the brain, really, that you can't easily make the reverse inference, like, oh, I'm seeing an activation there, therefore, this is what the person was experiencing. It really doesn't work in this way. It's much more complicated. So for example, you may have heard that the amygdala is the fear center of the brain. And in part, it is true. It is activated when people experience fear or anxiety, but that's only part of the story. The amygdala is also activated with positive emotions. So just seeing amygdala activation on its own is really hard to interpret. So for example, in the same study, they actually looked at the amygdala and they did find more activation in the amygdala in the expert meditators during this task when they were listening to a woman screaming in fear compared to novices. So does that mean they had more fear? Does that mean they had more compassion? Does that mean they were more in touch with their emotions? Like, it can mean an infinite number of things. And if we just look at this, we just don't know what it is that they were experiencing. So I'm going to now present another landmark study in the field, which was a study done by Wendy Hazenkamp, in which she looked at how expert meditators would practice focused attention meditation and then have periods of mind wandering and then focus again. So one thing that is well documented, actually, in functional brain imaging, maybe the most well documented feature, is the brain's default mode network. And what that means is that these are a set of brain areas that tend to become more activated when people are not engaged in any particular task. That's how it was found originally, is that it's what happened in between the tasks that people had to perform during these experiments. And later, it was understood that it is actually activated when people engage in mind wandering. So when they just start like thinking of their groceries list, of what they did the day before, what they would like to do tomorrow. So that kind of thing, that's when these regions tend to become a little bit more active than other parts of the brain. So Wendy designed a really interesting experiment in which she had people who were expert meditators practice focused attention on the breath while in the MRI scanner. And their task was to sustain their focus on their breath, and then at some point they would actually find themselves mind wandering. And as soon as they became aware of mind wandering, they had to press a button to say, oh, I was mind wandering right now. And then they would shift their attention back and then again try to sustain their focus on the breath until inevitably the mind wandering happens again. And so her hypothesis was that during the periods when they were mind wandering, she would see activation in the default mode network. And when they were actually applying attention or sustaining attention, that brain networks associated with attention would be engaged. And these are also very well-known networks in the brain. So when you look at this over time, the idea was that at the time the person pressed the button, she knew that right before then they were mind wandering. That's what it meant. And that right after that, they would be shifting their attention, and then shortly thereafter, hopefully be in focused attention again. Beyond that, it was unclear, right? Because at any time, they could have fallen back into mind wandering. We just don't know. So she only analyzed the data around the time of the button press, knowing that the 3 seconds before they pressed the button is when they became aware of mind wandering. Before that, they were mind wandering. And then after that, they were shifting their attention, and then they were focused again for a few seconds, at least. Does that make sense? Okay. And so what she found was fully consistent with these hypotheses. So if you look at here at the bottom, activation during mind wandering compared to shifting attention, these are exactly the areas of the default mode network. Then when she looked at focused attention compared to mind wandering, these were some of the, I don't know if you could see that, but there's some little parts of the turning the attention to an object. And then, so basically the top 3 rows are like different subparts of the attention networks. So, okay, mind wandering, the default mode network is activated. When paying attention, the attention networks are activated. Okay, so that's great, and it was replicated across the different participants, and it's beautiful. I'm going to argue, though, that this is not really teaching us anything new, neither about meditation nor about the brain. This is confirming that when people are trained, they can shift between these two, and you can see that in the brain. But is that really telling us anything that we did not already know? So that's one of the problems also in the field of neuroscience, is that, especially of neuroscience of meditation, is that the really good experiments are usually those that show us things that we knew. And then if we try to go beyond that, and if we try to test new ideas, it's much more difficult, and then we can fall into all of these different pitfalls. So this is something also that I want to emphasize and for you all to really think of. It is hard, okay? I love this paper. I'm a huge fan. I think it's beautiful. And I think it shows how limited we are right now in using these tools to study something like meditation. So another example, so this one is a study that I ran with Eric Schwartz, who I mentioned earlier. And we were looking at changes in brain response to emotional images after 8 weeks of meditation training. And so we had people just watch emotionally evocative images while they were in the fMRI scanner. And they had to just watch the images, and we told them, let yourself react to them naturally. So specifically, we did not want them to meditate because we were interested in their normal emotional response, and we wanted to see if that would be affected by having been trained in meditation. And these were all photographs of different situations with human beings in them, and we had a mix of positive, negative, and neutral emotional content. We were especially interested in the amygdala. As I mentioned earlier, the amygdala is implicated in emotional processing of both positive and negative stimuli. And previous studies found that amygdala response to emotional images decreased during a state of mindful attention meditation. But we wanted to test what happens when people are not meditating. Do the effects actually carry over to ordinary life? So here's what we found. This is looking at the amygdala response before the 8-week training and then after, so pre and post. We had a control group that did not meditate, and here we show activation of the amygdala in response to positive images in green, in response to negative images in red, and in response to neutral images in gray. So notice how both positive and negative images can engage the amygdala, as very well known from other studies, more so than neutral images. But there's no significant difference between pre and post in the control group, as hypothesized. There was one group that practiced mindful attention meditation. So not exactly mindfulness, it was a training based on shamatha practice. And here you can see there's an overall decrease in amygdala activation for all three types of images, although none of it was statistically significant in this small group of subjects. And then in the compassion meditation group, instead, we did find something different, because we found that the response to to negative images actually remained high from pre to post, even though the other ones went down a little bit. So there was an increased response to these images with negative emotion, which were images of people suffering. So what does it mean? So remember this problem with reverse inference. Like we can't just say, oh, their amygdala was more active, therefore they were more stressed or had more anxiety or fear or something. Just looking at this graph, we can't possibly interpret what was going on. So we need other data. So in our case, another thing we measured was levels of depression. So when we looked at how people responded to a questionnaire to measure their depression, the Beck Depression Inventory, we found that in the group that did compassion meditation training, the one shown in blue, the increase in amygdala response to these images of people suffering was correlated with a decrease in depression score. And this was not there in the group that practiced shamatha, or mindful attention meditation. There was no such correlation. Now, I don't want to make too much out of this because there was no main effect, remember? This is just the correlation between these two scores. There was no significant decrease in depression score. There was no significant increase in amygdala response. There's just this potential link between these two things that is intriguing. So really all we can say at this point is more studies are needed. And so one would actually want to design a study in which we look specifically at this question. After compassion meditation training, is there a significant increase in amygdala response to images of suffering? Can we replicate that, first of all? And then is there a link between that and a decrease in depression score? Okay, so I want to emphasize that in a study with a small number of subjects like this, in an analysis that was done post hoc, that was not one of the analyses we had planned beforehand, we cannot draw any strong conclusions. All we can say is, that's interesting, we need to investigate this further. Unfortunately, that's not how this is typically described, for example, in the media, or you will see many cases in which studies that are at this very preliminary stage are portrayed to the public as if they were conclusive and final and definitive. And this happens a lot in our field of studying meditation in particular, because it's cool. People really want to know what meditation is good for and what it does to us. And there's a lot of misinformation, unfortunately, that's based on things kind of like this. Like there's a small preliminary finding that gets really amplified, and then sure enough, a few years later, there is going to be a study that contradicts it, usually. And then, unfortunately, the whole scientific enterprise suffers from credibility issues, because it sounds like nothing that science does is legitimate, but that's not true. This is a preliminary study. This is not on the same level as like a replication study, one that has been posted with its methods by the NIH. Like there's different levels of credibility to scientific studies, and that is usually not well described to the public. So I want you to please keep that in mind, and that most studies that have been done about meditation are at the preliminary level. And we still need replication. We still need larger scale studies. We still need, much more. Okay. So this brings me to my next topic, which is challenges in brain imaging studies of meditation and possible remedies. So let's talk about reverse inference once more, because this is an important point. Again, the amygdala response to both fearful faces and happy faces looks very much the same. Therefore, it's not advisable to do reverse inference. If you see an image like this, you don't know if the person was looking at a fearful image or a happy image, okay? I just want to drill this one down. Now, there's other ways. If you want to know the subject's mental state, you can. Just ask them. Ask them what their first-person experience is. So this radical idea was bringing phenomenology into the neuroscience experiment, and that's what Francisco Varela actually brought to the field. And he called it neurophenomenology. So, of course, I'm caricaturing a little bit. It's not just asking people, hey, There are methods to do this very rigorously, actually, to really get very fine-grained data on their first-person experience and methods from phenomenology. So, for example, I'm going to show one experiment that he did that I thought was really brilliant, and we need more things like that. So this is based on using stereograms. How many of you are familiar with stereograms? Almost nobody. Okay, great. So the idea is, I don't know if this is going to work given this room setup, but you can always look it up online later. You have to to either cross your eyes or try to look out, as if really far out, until the two blue circles merge with each other or fuse with each other. And you're going to see 3 of them, basically. So if you're going to see 2, then you're going to see 4, and then at one point you're going to see 3. Does that make sense?
Yeah. It works.
So when you do that, then you might notice, if it worked for you, that now in the main image below, in this pattern, are 11 circles that are appearing. And they're appearing with some kind of depth, either in front or to the back of the main image, okay? So if you don't get it, don't worry. You can practice this later at home. But the idea is, so that was behind their 2002 study. They wanted people to first prepare or fuse, like what you did with the 2 blue dots. And then a stereogram would appear on the screen. And then usually it's not perceived immediately. And then it's perceived after a fraction of a second or a couple seconds. And once people perceive the stereogram, they have to press the button. And they measure their brain activity with EEG throughout this whole process. And they repeated it many times. Does that make sense? So here's where things didn't go as planned. They thought when you press the button, something happens, people perceive the stereogram, there's a moment of consciousness, of awareness, and we're going to see something different in the brain at that time. When they analyzed the data, it did not work. That was very noisy. Nothing happened at the time of the button press. And they were like, why is that? So they repeated the experiment, and this time they asked people to report whether they felt prepared at the time of when they were supposed to prepare for the fusion part, or they did not feel prepared. So a very basic first-person report. Are you ready or not? Okay? Yes or no? And now they reanalyzed the data using that variable, prepared or unprepared. And now they saw this major difference in brain activation between the 2 cases. What they found is that when people were prepared, before the stereogram appeared, there was not much activation going on, but then right around the time it appeared, already they started to see this long-distance synchrony between specific brain regions that then remained throughout as the stereogram was there. When people said they were unprepared, there was nothing at all, and even after the stereogram appeared, it took them a little while to finally get these long-distance synchronies, which are interpreted as this kind of moment of awareness, basically, or like this like recognition of something. So here you can see that really what was significant was not so much when the image appeared, but whether people felt ready to see it or not, that they had fused successfully. And so what they were measuring was really more a measure of preparedness in a way than anything else, right? And they could have never guessed that if they had not had this first-person report from the subjects, okay? All right, so there's been more neurophenomenology since then. So I'm embarrassed to show a slide from Judd, who is right here, Judd Brewer, who had a 2013 study in which he did real-time fMRI that also included subjective experience data. And in his case, he had expert meditators doing focused attention meditation. Basically looked at, for reasons I'm not going to get into today, but he focused specifically on this brain region, the posterior cingulate cortex, and used that to basically show people their own activity in this area on the screen. And so you can see it, for example, like if it's blue, it means it goes lower than baseline level, and if it's red, it means it goes higher than baseline level. So in this case, you can see, for example, in this trace that mostly it went down, like below baseline, which later, from correlating that with these participants' first-person data, was understood to be a good session in which they felt like they were indeed very focused. And so in meditators, expert meditators, they typically had these traces in which they were maybe a little bit in the red at the beginning, but then very much in the blue the rest of the session. Whereas here is a non-meditator who seems to be having trouble with the task and just keeps going up and down. And so can we do more than that? So in this study, so just looking at the data like that, you're just looking at a binary signal. It's either up or down, you know, red or blue. So that's one bit of information in computer science language. But of course, the first-person data is much more nuanced, much richer, much more precise. And indeed, that's what they looked at in a follow-up paper. And that's where they found that there were specific states that people described were associated with going into the blue, so to speak, versus going up in the red. And there were different clusters of states that corresponded to that. So looking at the first-person data brought more richness to the study. But I'm going to argue that the brain data itself also has untapped richness that is usually overlooked. So I don't want to give up on the brain data. Okay, the first-person data is great. We should totally collect it. It's hard, all of that. But the brain imaging data itself also has a lot of potential, and I'm going to show you something that I think is really fascinating about this untapped potential. So look at this for like a few seconds before you get bored. This is a flickering checkerboard, which is the most standard visual task in functional MRI because it strongly activates visual cortex, which is at the back of your head. And if you look at this for an hour, it would still activate your visual cortex as long as your eyes are open, even if you're really, really bored. And that's actually how people first did the very first fMRI experiment. They had this type of flickering checkerboard on for 60 seconds, off for 60 seconds, on again, off again. And they found in these really beautiful, I mean, for then, 1992, images that when you look during the periods of off, you see this kind of dark brain, periods of on, when the flickering checkerboard is on, all of that back of the brain, visual cortex lights up, as it shows on these images, and then in the dark again and on again. And you can look at it in time, and this is what it looks like. You know, it's like low activation, then high activation when it's on, and so on and so forth. And then what people then quickly did in the field is to summarize this type of data in a contrast map or an activation map, in which you just compute the difference, literally, between the on periods and the off periods. So here, if you do these on minus these off, you're going to see something like this. This one is higher res because it's a more modern study, but the same idea, okay? Now, what is the problem with this way of doing things? Is that it looks as if only this part of the brain is active. And it looks as if the rest of the brain is just dead, right? As if it's completely inactive, doing nothing, sleeping, taking a nap, whatever you want to call it, and only this part is actually awake and doing something. That is not at all what is going on. If you look at the intensity levels in these images, you see that in the off period in the visual cortex, it's a level of 5,750 in whatever units they had. When it's on, it's 5,900. How big of a difference is that? Well, it turns out that the level, the percent change in the bold oxygenated level dependent signal is a few percent at most, okay, in every functional MRI study. And in fact, in psychology study, it's even lower. It's usually less than 1%, okay? So that part of the brain is very much active, thank you very much. Then it gets a little bit more, and significantly so, and we can measure it, and we can map it, and it's great. But let's not forget that this is not zero, okay? So this has actually been done now with more modern methods in which you relax the constraint that you use this particular hemodynamic response function as your model fit, which is what everybody does, okay, myself included, you know, when we do fMRI studies. When you relax that and you allow other shapes, you see that every part of the brain is activated by something as boring and stupid as a flickering checkerboard, okay? In a way that's very repeatable. So this is also not noise. All of these things, if you scan people for 20 hours, which they have done, not in a row, but over many days, they get consistently the same activation, the same shape, and it's in the whole brain, okay? So we clearly have more work to do because the whole brain is active all the time. We just haven't measured it right. And the authors have very strong things to say to the field, so I'm going to read it because I think it's really essential. Despite converging evidence suggesting the whole brain is continuously working and adapting to anticipate and actuate in its response to the environment, over the last 20 years, task-based functional MRI have emphasized a localizationist view of brain function, with fMRI showing only a handful of activated regions in response to task stimulation. Here we challenge that view with evidence that under optimal noise conditions, meaning they scan people for 20 hours, fMRI activations extend well beyond areas of primary relationship to the task. And bold signal changes correlated with task timing appear in over 95% of the brain for a simple visual stimulation plus attention control task. These findings highlight the exquisite detail lying in fMRI signals beyond what is normally examined and emphasize both the pervasiveness of false negatives in which, oh, well, my task did not activate this, the brain, and how the sparseness of fMRI maps is not a result of localized brain function, but a consequence of high noise and overly strict predictive response models. Basically, we're looking at it the wrong way. It's not that it's not there, okay? So now, given that neuroscience is still a work in progress, I want to point to a few things that may sound like neuroscience, but today is really not neuroscience, at least not yet. So for example, you may have heard of a device called Muse that describe themselves on their website as a brain fitness tool that measures brain signals much like a heart rate monitor senses your heartbeat. Sounds great. Really? So here's the heart, okay? Here's a heartbeat signal. If you put two electrodes here, or here, or here, or here, you're gonna get pretty much the same because these are driven by cardiac pacemaker cells, and this is a very stereotypical signal. It's always kind of the same shape, you know. It's simple to measure, relatively. And if there are any cardiologists in the room, I apologize, because I'm sure it's more complicated than I know, but this is not the same than measuring brain activity from EEG, even if you have 100 electrodes, which this device doesn't, it has 2. You have all of these traces of all of that stuff. Like, what do you do with that? Not to mean that it's impossible to analyze, actually, you know, it is. But what is it that you're trying to measure? Like, which part of the brain, which, you know, like, so it doesn't make any sense to say that you can measure your brain the same way that you can measure your heart. It just doesn't make any sense. So another thing similar, in my view, is combining meditation with brain stimulation. Like, for example, transcranial direct current stimulation. Really? So this is actually an old idea. The idea of stimulating the brain with like 2 electrodes, and you like basically zap current in there, and that will indeed throw some neurons off and do something. It's definitely doing something. In fact, already in the 1800s, they had another name for it. It was called brain galvanization. And at the time, it was the latest thing, electricity as a medicine. So we're just rediscovering this today, which is, you know, I think pretty funny because we have, you know, we should have better technology, but, you know. Of course, there are safety issues, of course, because no brain stimulation technique is free of side effects. If you are going to be affecting your brain, how could that possibly be without any side effects? So you could burn your skin, but you can also get working memory impairments, as has been found in some studies, or even potentially induce seizures. And so people who have reviewed this, and their paper is called Non-Invasive Brain Stimulation is Not Non-Invasive, just in case you didn't get the message. There's too many risks from basically known unknowns. So unplanned effects from buildup of stimulation effects, meaning either it propagates to other brain areas than the ones you plan to target, or over time if you do too many sessions, but how many is too many, we don't know yet. And then, of course, you know, inducing long-lasting changes in cortical excitability can be dangerous, and that means that the brain will adapt to this kind of constant or like dysregular stimulation, and then who knows how it's gonna affect it in the long run. In any case, does it even work? Like, does it even do anything beneficial? What's the evidence? Again, you know, a paper titled Questionable Science and Reproducibility in Electrical Brain Stimulation Research does a good job at showing all the possible problems, all the ones they found, actually, questionable research practices in the published studies. And they conclude the belief that electrical brain stimulation is effective needs to be replaced by a more rigorous approach so that reproducible brain stimulation methods can be devised and applied. So it's not to say that brain stimulation should not be used. Absolutely not. I think, for example, ECT is a very important tool in psychiatry. And I think that it's just a matter of doing the right kind of research and not getting ahead of the research, not starting to use these devices that have never been actually tested or not appropriately before, first of all, they're determined to be safe, or at least safe under certain conditions for certain populations, and then that they do have benefits. There's other issues of variability between subjects or within subjects. Just because it worked for you yesterday doesn't mean it's going to work today, etc. I'm not going to get into this. So now, beyond the hype about meditation, how can we improve research quality? So one concept that has been often touted also in the field is the dose response, like for a drug. So for a drug, if you take more of the drug, you get more of the therapeutic effect up to a point, and then there's a point at which it becomes adverse effects, right? So the question is, should we expect a similar relationship between meditation dose and its benefits, and then on its harmful effects? So we don't know. We don't know. We don't know. Let me say that again. We don't know. Okay? Like some people will tell you, oh, if you meditate more, it's better. It's like, we don't know. That hasn't been studied really rigorously. Why? Well, one of the issues, not just for dose response, but more generally, is that there is a bias in science that null findings typically don't get published. So if you run your study and then in the end your patients didn't get better, for example, the tendency is to not publish it at all. Why? Because most good journals will actually refuse to publish null results, like a lack of a significant effect. Why is that? Well, it's because it's actually very difficult to conclusively prove a lack of effect, because it could be due to your sample being too small or you had some methodological problems. So we don't really know what happened. It's like you have a null result, it's hard to interpret, and you can't really say, oh, therefore this intervention didn't work. And so because of that, studies with null or negative effects are not published. In the field of meditation, it's especially problematic because it's possible that a majority of studies end up being null findings or negative findings, and we just never know because it's not published until you talk to people and you hear that they have some things that they have not been able to or willing to publish. So this is one other thing to keep in mind. If you say, oh, but there are 10 papers that found that meditation X did this benefit, okay, but how about the 30 that tried it and who did not find an effect? Until we really know this, it's hard to draw conclusions. There are methods in meta-analysis to account for the potential lack of publication of some of these findings. So you will see that in some meta-analysis paper that they check for like a skewed distribution, for example, of outcomes. But anyway, so that's definitely a problem beyond just meditation science, but more generally. Also, and here I'm going to point to Wilby and Jared, who are here, who do some amazing work on this, the fact that meditation practice can have negative or adverse effects. And so they have this paper that they published a couple of years ago now, wow, that I highly recommend because you'll see that some examples of reported potential negative effects are depression, anxiety, panic, somatic problems like painful sensations, poor digestion. And these did not only occur during intensive retreat. That's also one common misconception that, oh, well, as long as you don't do like 20 hours a day, then you're fine. But it seems it's not that simple. So, I think, so we don't know yet how prevalent these problems are, because these were people who volunteered to talk about them. They're probably not the only people in the world with this problem, but what is the actual distribution? How often does this happen is unknown, and what needs to be done in the field is to actually measure this much more rigorously so that we have a better sense for their prevalence and also their severity, and also then what to do about it. So some of the questions, I think, for the field that they propose, and I fully agree with, are, can adverse reactions happen to healthy people? Or is it only in those with pre-existing mental health issues or history of trauma, etc.? Are these problems caused by incorrect meditation practice? Or are they normal stages on the path, as some traditions will say? So these are all questions that have not yet been addressed scientifically. So in the interest of time, I will not get into trauma-sensitive mindfulness, but I would totally encourage you to speak with Willoughby about that, because she's the expert anyway. But yes, there are people who are trying to teach mindfulness in a way that is trauma-sensitive and will hopefully reduce the adverse events. Finally, I want to go briefly through some prescriptions, some recommendations for the field from research on mindfulness and meditation that was published by Van Damme and colleagues. And so let me get to it. There's various possible meanings of mindfulness that have not been clarified. There's all of these issues from the replication crisis in psychological science. So as I mentioned earlier, pre-registered experiments, open science replications, we need that in our field too. In clinical trials, we need more uniformity of what is taught in the mindfulness interventions, better designs for control group, and again, measure unreported adverse events. Also, when it comes to neuroscience, remember, neurosciences are complicated. New findings from contemplative neuroscience about the mental processes and brain mechanisms of mindfulness practices must be reported with all due modesty, in the author's words. I think it's beautiful. I think that's what the field lacks a little bit. And that their importation into protocols for future clinical practice must await proper vetting of their potential practical significance. I'm not sure if this is even possible at this point, but we need to say that this is necessary. Finally, just saying something is happening in the brain, that's no longer sufficient. Like, we don't know if that something happening is important or even beneficial. So we need to be doing better than that. So in summary, when you talk about the neuroscience of meditation, there are various questions and intentions, various methods. So one of them is, for example, trying to understand the hard problem of consciousness. That's what Varela was after. That's how he founded neurophenomenology. These days, it's more about testing the benefits of meditation training in terms of physical health, mental health. So that would be part of the current mindfulness movement. Looking at it in short terms, long term, like lifelong, and then are these treatment for known pathologies, or is it more general enhancement of well-being? How about social benefits? And then finally, unfortunately, but I need to say it, it can be used as a sales pitch. Neuroscience can very much be used to sell you wellness programs, retreats, apps, technology-enhanced meditation. Remember the electrical stimulation while you meditate. And so I just want to warn people about this and to not take anything that sounds neuroscience-y as really necessarily legitimate. So for future research, I would recommend to study both the underlying brain mechanisms of meditation, such as mechanisms of attention, interoception, self-related processes, compassion, and also the health benefits. So this dose response, like, is dose even a relevant concept? We don't even know that. What types of meditation practice? Then if one had to choose between meditating and going to the gym, like, what should you do? It really depends what your goals are. How about sleep? Everybody's sleep deprived in this culture. So that's also not something to forego to add meditation to your routine. And then some of the questions that I've been collaborating with investigators here and elsewhere are on the science of behavior change. Like, does meditation help with engaging in healthier behaviors in terms of diet, exercise, sleep, addiction, and so on and so forth? Can meditation impact disease predisposition, other complex traits, knowing that much of trait variation is actually genetic? So how much do we leeway do we have? And finally, again, is meditation safe or beneficial for everyone? So these are just some questions for future research that I'm interested in, and that I hope people will consider as the field grows and mature. So thank you all very much for your attention, and these are my acknowledgements, and I'm going to take questions if you like.
That's a good question. I love your question about is dose even a relevant concept. What other concepts would you throw in there? So whether it is or isn't, what other things are you thinking about in that category?
Oh, there's many. There's many dimensions in which we don't even know if it's relevant. You know, like, do you need a live teacher? Do you need a live group? Or can you learn remotely or on your own or from like some other system, you know? Yeah, like every aspects of the practicality, like does it matter to sit on a cushion versus sit on a chair versus lie on a bed? You know, these are all, like, many people have strong opinions about those, but there's no scientific evidence about that, none whatsoever, as far as I know. I mean, if there is, let me know, but I don't think there is. So I think there are many things we should study. Yeah. Yes?
To the extent this is something of a cautionary tale for us, are there particular things that you think have been overhyped? I mean, name your top three, I guess, in terms of you know, the benefits of mindfulness or the benefits of meditation or the neuroscience-based values. What are we being fed that we ought to be really?
I don't want to pick any particular points, because the thing is, the global message is we don't know yet. You know, maybe some of these hype is actually true, but by chance, you know, like we just don't know yet. So I think it's more a matter of remaining very open-minded, you know, like hearing all of these claims and being like, okay, you know, let's see, you know. And also I would recommend people just follow their own experience, you know, like their own experience with whatever it is, you know. If it doesn't feel good or right, or if it seems, you know, then maybe take a step back, talk to other people, you know, maybe it's okay and you can, you know, get past that, but then maybe there really is a problem, you know. So I feel like people will sometimes ignore, you know, their own lived experience just because somebody else said, but it should work, but it will work for you, you know. And I think that's a problem. I think it's more about re-empowering people to just not follow the pseudoscience, like, you know, it's like, this is just, you know, more like noise, you know. Don't believe it too much. I think that's more like what I'm trying to say. Yeah.
You know, you reviewed neuroscience research and you pointed out all the problems. But at the end, I mean, there's a whole other body of research that isn't neuroscience on the effects of meditation. And not that I know that research that well, but I would imagine a lot of it doesn't have the issues that you're pointing to with neuroscience, and there might be valid studies on the effects of meditation that isn't using neuroscience as proof.
Yes, thank you. Yes, indeed. This talk is really focused on the neuroscience piece of the field. I think in clinical trials where the measures are clinical outcomes, for example, do people, symptoms of depression go up and down, you know. I think there are methodological things to consider too, but it's different. And I think there's been so many of these that, at least in some realms, there is evidence that seems fairly believable, you know, according to recent meta-analysis. And, you know, it's not that earth-shattering. Effect sizes are small to medium. Usually they find that mindfulness, for example, or like, you know, is on par with other existing therapies, is not superior, or at least there's no clear sense that it would be superior. I think superiority studies have not been done, so that's different. But just the effect sizes are like, in line with other methods. So then it's more a question of why would that be more beneficial, maybe for other reasons that were not measured. Like if we measure depression symptoms, that's great, but do we measure people's sense of purpose in life, or like other things that are just more, hard to measure, that don't appear in these data? And also, even if the effect size is the same as, say, individual psychotherapy, well, individual psychotherapy is not available to a majority of people because it's too costly and there's not enough therapists. So even if there's just that, like it's scalable and it's cheaper, that by itself could be have a major impact on public health. So I think we also, it's not just all about the effect sizes either.
Hi, thank you. I have a question about the point you made about the first fMRI study, which looked at one region and then it was replicated, and in 2012, and then it showed that there are multiple regions that are affected.
Yeah.
And I was wondering, why aren't fMRI studies more comprehensive, and why don't they include more regions? Is it a hardware problem? Like, this is a very basic question of the fMRI. Is it like a problem with the way the design of the study was made, or is it a problem with like cost? Is it much more expensive to look at more brain regions?
So it's basically a problem with cost, not in the sense that basically it is the fact that the visual cortex is much more activated than the rest of the brain during these tasks, but it's just not uniquely activated,
Right.
So I think I said it's less than 1%. With the other brain areas, it's even less than that. It's like so small that if you scan people only once, like for an hour, you can't see it because the data is too noisy. So the trick here, when they managed to see all of this in the whole brain, is that they had to scan the same person for like 20 hours to have enough signal to overcome the noise in the bold signal, and then do this analysis and be able to see this.
Okay.
So it's, in a way, it's like you don't want to do this for every possible experiment because inevitably you're going to find the whole brain every time. And that's not interesting, like every time we need to study a specific question and look at, like, have a hypothesis perhaps, like this brain area will become more or less active, So we don't need to do this every time. This was more like a demonstration to remind people, that the localizationist view of the brain is wrong, which any, neuroscientist would know, but we keep forgetting because we look at these images, and we're like, oh, visual cortex, visual stimulus, and then we forget that the rest of the brain is still active. Yeah.
You talked at one point, I think in the context of the default mode network, about how it showed that there were attention, places in the brain that were associated with attention. I'm wondering if there's been any research on different types of attention,
Yes.
like concentration versus like more open awareness, and whether those show different.
Yes. Yes and yes. People have done that, and there are differences in the brain areas that are involved. Again, it's still very preliminary research. It's still, But yeah, it seems like those are different.
When you're talking about sort of misrepresentation of a lot of this data in popular media, I'm always curious whether you have any advice for people who are academics or researchers, whether in the broader field of investigating meditation generally, or specifically in neuroscience, if you're only comfortable speaking to that, of what we can do to be more responsible in our methodology and in creating these studies, and what we can do. We have very little control, obviously, over how these things are represented after the fact by people writing bias articles, but it's also, I hope that there is some things that we can do to be more responsible researchers and to be able to sort of minimize the amount that research can be misrepresented, after the fact in more pop cultural claims.
Well, there's two levels, right? The first is do your work correctly, and that's actually more difficult than it sounds. In all of these studies, it's not like there's one good way and many wrong ways, and it's much more complicated than that. And if you talk to different experts, they're going to recommend different things. So it's not always easy, not to mention the lack of resources, to run your study in the way that is scientifically the most sound and the most robust. So there's that. Then there's the communication of the findings. And so that is tricky, like I think some scientists have gone so far as to create their own platform to basically talk about their research in lay people terms and like blog or have ways to basically bypass the media machine in which there's so much hype and not everywhere and not all the time,
Do you think that's a successful approach, or has been, or?
I have no idea. I haven't followed what happened with that. I don't know. But yeah, those are really important questions. Yeah. And educating the public. The public should also be able to know when they read something if it's legit or not. You'll have a sense for it,
Right.
Yeah, stuff.
Thank you.
Yeah.
I don't know if I can quite say this correctly, but I have this question. Everything you know, and I'm assuming you also practice meditation a bit, is about, from a scientific point of view. Everything you've reported is from a scientific point of view. So putting that aside, if someone came to you and said, I want to be a better person, and I want to wake up the way the Buddha taught, what would you say to them?
Find a teacher.
And give it a try?
Yeah, but don't try this at home,
Don't try it at home?
Yeah, I would not recommend that. People can do whatever they want, but I would not recommend try this at home. I would say find a teacher.
Thank you.
That was a very beautiful question. It goes to the very existential condition that we're all in. Does modern science still equate mind with brain? Have they made a distinction?
I think as a neuroscientist, I have to tell you that the mind is a product of the brain, and that's it.
There's no possibility for a little philosophical Buddhist wiggle room?
Well, then that's beyond the realm of science. I believe in the non-overlapping magisteria, so I'm just going to say that's something else, and I'm not here to talk about this here publicly.
But we are integrated to a level which I think even in the strictest of academic settings you couldn't refute the necessity to abridge both sensibilities regardless of their academic discipline or their spiritual soteriology, if you will.
That's right. And I do collaborate with contemplative scholars. That's all I can say.
If there are no other questions, please join me in thanking Dr. Schwartz.